Hi, welcome to this webinar on rapid control prototyping for power electronics and motor control. My name is Carlos Villegas, and I am the Electrification Industry Manager at Speedgoat, where I look after real-time solutions for power electronics, motor control, battery systems, and power systems.
And this is Diego Curatle. I work at MadWorks in technical marketing for real-time testing. Here are the key takeaways that we would like to share during this webinar. First, rapid control prototyping is a development phase that allows reducing risks when commissioning complex controls for power electronics and electric motors. Second, you can use auto-tune features that enable a straightforward transition from desktop simulation to testing with real hardware. And third, a scalable and powerful platform is required when prototyping power electronics control designs, and Speedgoat offers a mature hardware technology to satisfy those needs. Talking about technology, Carlos, you are the industry expert here. Can you tell us what are the typical market trends and the challenges that electrical engineers are facing when developing controls for power electronics?
Sure, Diego. Power electronics currently experiences a very strong growth in part due to the use of more renewable energy sources and a relentless increase of electric transportation. On electric transportation, electric buses, cars, bikes, and scooters are now common in many countries, and even air taxis are making progress. Even some analysts are targeting around 2050 when wind, solar, and electric vehicles will overtake their fossil fuels counterparts. Maybe simulations and model-based design will support us reaching these milestones even sooner. At a component level, the use of wide bandgap semiconductors like silicon carbide and gallium nitride are leading to more compact and efficient power converters. At the same time, using wide bandgap devices significantly increase the bandwidth and switching frequencies of controllers from a range of tens of kilohertz to all the way to several megahertz. Such high frequencies are making more engineers use field programmable gate arrays or FPGAs. Another driving factor comes from control algorithms. Complex controls, algorithms, and signal processing also increase the processor requirements for embedded platforms. While strategies with adaptive controls, Kalman filters, or model predictive control may work very well in simulation, testing them with your hardware may lead to delays as you typically have to deal with fixed point implementations, data, word size, limited processing capacity, or the inherent complexity of implementing control protocol stacks. Often, the algorithm will simply not run at the required sample time. Furthermore, more control engineers are considering machine learning or even deep neural networks, leading to even larger processing requirements. Therefore, there is a drive towards larger processing capacity, flexible control platforms, and turnkey communication protocol functionality that support control engineers to successfully commission their control algorithms with their power electronics or motor control hardware. This was just a general overview of some of the challenges we know that engineers face when designing and testing power electronics controllers. Diego, could you tell us how to address these challenges?
Yes, Carlos. There are several benefits when adopting rapid control prototyping. Our final product will probably require an embedded board with a microcontroller or FPGA. We will have to select the right chip depending on the size of the code, the switching frequency, and the required I/O channels. These are many requirements to validate, and we don't want to wait to have the embedded board available. With rapid control prototyping, we introduce a hardware platform that is independent from the final embedded device. It will be a real-time computer that we connect to our power electronics component. So we can validate the requirements before we start the design of the hardware. As a consequence, we can find design errors very early in the development phase. Some mistakes can be found also with desktop simulation, but we know that testing on hardware can introduce new variables. As we are validating and finding mistakes, we might need to change requirements. This can be easily done when using a rapid control prototyping platform. We can also integrate new components. For example, if the project scales up, we can add I/O channels to the hardware configuration. And this doesn't require to redesign the embedded hardware. So we are not affected by hardware revisions, but also we don't have to think about firmware updates. We can tune parameters and log data, and we can do that easily using MATLAB and Simulink. And the advantage here is that there are built-in functionality available, ready to use. We don't need to configure the file system. We can add communication interfaces, and also in this case, we can use built-in functionality. We can simply use driver blocks and keep the focus on the control algorithm. Eventually, we don't have to think about accessing onboard memory and I/O registers. Configuring the registers of a microcontroller or configuring the memory access for an FPGA, it's always time consuming. If your requirements change, then you might have to change the chip, and you will probably have to configure again all registers. Setting up registers and memory access is something that we want to do once all requirements are well validated. In other words, with a rapid control prototyping platform, we can be independent from the embedded hardware. Control prototyping is a development phase where we want to focus on the control algorithm. Once we have defined and validated the control algorithm, the switching frequency, the required I/O, only at that time we can move to the embedded hardware. We have talked about this rapid control prototyping platform, so let me show how it looks like. First, we need a device to test. This can be a power converter or an electric motor. Then we have the development computer. Here we can design the controller. We can run desktop simulation and then integrate the I/O driver blocks. We need MATLAB, Simulink, MATLAB coder and Simulink coder for the automatic code generation, and Simulink Real-Time. And finally, the missing piece, the real-time computer. This is provided by Speedgoat. We will talk about this later. Essentially, the development computer is connected to the real-time computer with an Ethernet connection. The real-time computer runs the simulation in real time, and it's connected with analog and digital lines to the device under test. Now, let's see how we can deploy the control design onto a CPU or FPGA. The real-time computer includes a CPU, for example, an Intel Core i7 quad-core, and one or more I/O modules. Those modules could have fixed functionality, for example, 32 analog inputs or 4 CAN channels, or can be reconfigurable and even programmable. This is where we introduce FPGAs. When we need closed-loop sampling rates up to 20-30 kHz, the control algorithm can run on the CPU. This means that we generate C code from the Simulink model, and we build a real-time application that runs on the CPU. For high-resolution PWM signals and fast-switching components, we use an FPGA. The good thing is that we don't need to think about the FPGA. We would simply add and configure a PWM block in the Simulink model, and this will take care of setting up the signal generation on the FPGA. Now, one problem is that the communication bus between CPU and FPGA requires some communication times. Typically, it's around 1 or 2 microseconds for each 32-bit read or write operation. If we use analog inputs with 16-bit resolution, you can quickly find out that this will limit the achievable closed-loop sampling rate. That's why I was mentioning 20-30 kHz before. There is the possibility to execute the fast closed-loop control algorithm in the FPGA. We still use the CPU for slower components of the control design, but we can generate HDL code, synthesize, and run the hardware implementation in the FPGA. That's typically much faster as we exclude the CPU FPGA communication times at every sample step. That way, the control algorithm can directly talk with the inputs and outputs. But let's take a step back. I'm going to show how things work, and then Carlos will do some live demonstration. We have a Simulink model that we have used for desktop simulation. First, we will have to apply a model configuration that enables code generation for Speedgoat. For this, we can simply use the Simulink Real-Time app. This will automatically set the right configuration. Then we add the Speedgoat driver blocks. For example, PWM generation, analog inputs, quadrature decoder. We configure those blocks directly from their mask in the Simulink model. In the Real-Time tab, we can connect to the Speedgoat target computer and select Run on Target. This action will automatically generate the C code, build the real-time application, download to the target computer, and start the execution. This is what we call one click from desktop to real-time simulation. As an alternative to achieve faster closed-loop sampling rates, we can use HDL coder and target an FPGA. For this, we can select the subsystem with the fast control loop, right-click on the subsystem, select HDL code and HDL Workflow Advisor. This will open the HDL Workflow Advisor, which guides us through the model configuration and optimization to generate HDL code. Speedgoat provides packages with built-in configuration that automatically set all parameters to target the Speedgoat FPGA boards. While going through the HDL Workflow Advisor, we will have to manually map the physical I/O pins of the FPGA with the inputs and output ports of the subsystem. At the end, we will get a model with one part that will be deployed to the CPU and one part to the FPGA.
Thanks, Diego. That gives us a great overview of the advantages of rapid control prototyping. Let me try to illustrate the main advantages of rapid control prototyping that Diego just mentioned. Let's say that we have a permanent magnet synchronous motor and we want to do speed control under different load conditions. We also have the motor datasheet from the manufacturer. In this case, we are using a permanent magnet synchronous motor with a 100-watt rating, 7 pole pairs, 24 volts nominal voltage, and a rated speed of 4,300 RPM. Our final motor drive is still under development. As we will use a standard 2-level 3-phase inverter topology, we'll start testing with an off-the-shelf inverter from Speedgoat. After checking that the technical specifications of the Speedgoat 3-phase inverter are suitable for our test, we'll use rapid control prototyping to make sure that our control strategy and motor can achieve our project's requirements. As a motor control approach, we'll be using field-oriented control. Let me show it to you within Simulink. Here is our Simulink model for desktop simulation. The two large blocks in the model are the control algorithm on the left-hand side and the plant with a motor, drive, and load on the right-hand side. If we look into the control algorithm, we'll see the field-oriented control blocks, including the typical Park and Clark transforms, to go from the 3-phase coordinate frame to a rotating DQ coordinate frame. Once we're happy with the simulation results, we will take the control algorithm that you have just seen and deploy to the Speedgoat baseline real-time target machine. This simple diagram summarizes the interfaces between the control on the left, the drive, and the electric motor on the right. The control algorithm running in the baseline real-time target machine will obtain the rotation from the quadrature encoder sensor. It will also measure the phase currents by using analog signals, and finally, it will generate PWM signals to the motor drive in order to control the electric motor. We'll configure all interfaces from Simulink. As Simulink Real-Time is jointly developed by MathWorks and Speedgoat, transitioning from desktop simulation to testing could not be easier. Let me show you how it looks in the product. Here we have the blocks for the field-oriented control algorithm. We'll configure the real-time deployment from within Simulink, like the multi-core execution, sample time, word size, and the format for each signal. For example, here we have set 20 kHz sample time for the inner current control loop shown in red, and we also set a slower 1 kHz sample time for the speed outer control loop shown in green. We configure the FPGA and input-output interfaces from within Simulink. Here we select an IO397 FPGA. We use a predefined bitstream built to our needs that includes an input for encoder measurements, 3 PWM channels, an interrupt, and also general-purpose digital I/O. We're also using analog inputs for the current measurements. Now we also add a PWM generation block from the Speedgoat library. We set the number of channels to 3, define a symmetric PWM pattern, set the switching period, add a PWM trigger, and set the sample time to 50 microseconds or 20 kHz frequency. The 3-phase duty cycles will be an input to this block. In a similar way, we can add and configure digital outputs for starting and stopping the motor. It is also easy to instrument Like here we can add a switch with a few clicks. We can now connect, deploy, and run the controller to the target, and the motor will start spinning. We are first just spinning the motor with scalar control. We basically provide three-phase sinusoidal voltages whose amplitude and frequency will create a rotating magnetic field that will also start rotation of the permanent magnets in the rotor. As the motor spins, we will be measuring the rotor rotation and three-phase currents using I/O configured with Speedgoat driver blocks that we create in a similar way as we did before for the PWM generation and digital channels. We're now commissioning our input and output interfaces with the drive and electric motor. Let us run the model again and plot the current measurements in real time using Simulation Data Inspector. We then realize that there is a significant bias in the current sensors as we have not calibrated them. We can now go to the ADC transducer voltage to current signal conditioning block and modify the bias vector to remove this offset. As we are running the model, we immediately notice that we have removed the bias of the sensor. Now that we have removed the bias, let us try spinning the motor again. We measure the current and we can notice that there is no bias anymore, and as the motor starts spinning, we now have a three-phase current centered around 0. We can also see the rotor speed from the encoder measurements. We can also log data that we will have on the screen and compare with different test runs to evaluate performance. We can also compare the performance of different control algorithms or test conditions. We can then see how easy it is to configure real-time execution, connect inputs and outputs, modify parameters, see waveforms, and also log data from Simulink. But we don't want to just spin the motor, but to test a closed-loop field-oriented control algorithm. We have already added input and output interfaces using Speedgoat driver blocks to the field-oriented controller, just as we did before with the open loop example. We also use a graphical user interface in the Simulink editor to control the motor and plot the speed. We build, deploy, and run the closed loop algorithm to the Speedgoat target computer with a few clicks. It is initially in standby state, and we transition to closed loop state with a switch enabling the PWM gate drives. The rotor speed rapidly reaches the speed set point. We adjust the speed with the rotating knob, but we could also have done it in other ways, like with the command line or programmatically. We see some overshoot in the tracking performance of the speed tracking. Let us tune the control gains using a graphical user interface that we created and double the P gain or proportional gain of the velocity PID. We can go back to the other user interface and check the performance by adjusting the speed. We should expect for the control performance to be a little bit different than in desktop simulation. Nevertheless, we can always tune the parameters in real time to achieve the desired performance. But we don't really want to spend much time doing manual tuning, especially when we have cascaded control loops and 3 different PI controllers to adjust. Wouldn't it be excellent to have an automated approach for tuning? We can do this with the FOC Auto Tuner from Motor Control Blockset. Unlike embedded platforms, Speedgoat target computers have sufficient processing capacity to handle complex auto-tuning algorithms during real-time testing. This is a FOC Auto Tuner block. Here we can set the control requirements and the Auto Tuner will find all the control parameters automatically. In this case, we set the control bandwidth and phase margin for the inner control loop and outer control loop. The auto-tuner will apply perturbations to the speed and current control signals and use the response to obtain the right control parameters. Let us build, deploy, and run the field-oriented control to the Speedgoat target machine using the FOC auto-tuner. We can see the significant response improvement after the perturbation signals are used for tuning. With the PI parameter obtained for both control loops, we get a much better performance. The PI parameters are updated within the controller in real time. We can also see the resulting gains with the Simulation Data Inspector or just using a display during desktop simulation. With the advent of wide bandgap semiconductors and to reduce noise for electric vehicles, the control bandwidth requirements are increasing from a few kilohertz to at least tens of kilohertz. Algorithms are also becoming more complex and require faster signal processing capabilities. We can use FPGAs for those faster control or signal processing needs. One way of implementing our field-oriented control to the FPGA is using an efficient fixed-point implementation. We can convert the controller we had already to a fixed-point implementation by using the Simulink fixed-point conversion tool. Nevertheless, we can also stay in floating point thanks to the native floating point support in HDL coder. We can even implement algorithms with large or unknown dynamic ranges and implement operations that are difficult to design in floating point like the arc tangent. With floating point, you are also able to analyze the VHDL code generated by your model. It is possible to go to the VHDL implementation of any Simulink model that you're interested on, so there is full bidirectional traceability. Now that we have illustrated the advantages of rapid control prototyping with an example, Diego, could you tell us which are the software and hardware products that we need?
Yes, Carlos. As you said, we need software and hardware. And here we have two companies, Speedgoat and MadWorks, that work together to provide a real-time testing platform for MATLAB and Simulink. On the hardware side, we have the Speedgoat real-time computer. On the software side, we have MATLAB and Simulink. For code generation, we use MATLAB Coder and Simulink Coder. We can see Simulink Real-Time as the gateway between the control prototyping hardware and the MATLAB and Simulink. For example, Simulink Real-Time enables the use of the MATLAB API and App Designer for building user interfaces to control the real-time application running on the Speedgoat computer. We can use Simulation Data Inspector and Simulink External Mode to log data and tune parameters. But there is also further integration and full compatibility with many other products. For example, Simulink Test that enables test automation workflows, Stateflow to develop control logic, Motor Control Blockset that includes examples that are ready to run on Speedgoat, Reinforcement Learning Toolbox and Robust Control Toolbox if you want to explore new techniques for your controls. Simulink Control Design that includes the auto-tuner block that Carlos showed before. And HDL Coder, as we have seen, to generate HDL code that can run on Speedgoat FPGAs. Now, on the hardware side, there are mainly two real-time computers suitable for rapid control prototyping for power electronics and motor control. The Performance Real-Time Target Machine is a 19-inch rack system. It's very scalable and it can include hundreds of I/O channels and offers the highest processing power. It can be equipped with the last generation multi-core Intel CPUs and Xilinx FPGAs. If you are looking for a smaller platform, you should consider the baseline real-time target machine. This system can be equipped with a fair number of I/O channels. It's ideal for use in the field, but it fits well on a desk too. In those real-time computers, we can install analog I/O modules, for example, analog inputs to measure phase current at high switching frequencies, I/O modules with frequency input and output signals, such as PWM generation, encoder and resolver measurement, and communication interfaces, such as SPI, I2C, CAN, Ethernet, and Modbus. In some cases, one single I/O module can combine multiple functionality. For example, the IO334 is an FPGA-based I/O module optimized for the use with HDL coder. It includes a combination of analog and frequency I/O channels. It can also be connected directly with other I/O modules with fast multi-gigabit transceiver. Speedgoat can also support us with power conversion and signal conditioning. The Speedgoat three-phase inverter can be used as an interface to small electric motors, but there is also the possibility to integrate higher power devices, for example, power converters supporting 800 volt, 24 amps, and custom switching frequency. Carlos, can you show us a few examples of the use of those products?
Sure, Diego. Let me try to illustrate how to use the products with two examples. One DC-DC converter and one grid-tied three-phase inverter. Let us say that we want to design a digital controller for a DC-DC power converter that regulates the voltage to light the LEDs in a car headlamp. We use the SEPIC topology, where SEPIC stands for Single-Ended Primary Inductor Converter. This is essentially a boost converter followed by a buck boost converter and can increase or decrease source voltage as needed. SEPIC converters typically require very high frequencies in the range of hundreds of kilohertz. We'll use rapid control prototyping as we want to develop and test our control algorithm as fast as possible. We also want to adapt the control, tune the parameters, and measure data on the fly from Simulink. By using Simulink Real-Time and Speedgoat hardware, we'll aim at automatically generating C or HDL code and configure all inputs and outputs from Simulink with Speedgoat driver blocks. For rapid control prototyping, we'll use a baseline real-time target machine with an IO397 Simulink programmable FPGA. This I/O module from Speedgoat has a Xilinx FPGA analog input and output channels as well as configurable digital I/O lines. In this case, we will be using the analog inputs and the PWM functionality to generate a 100 kHz switching frequency. With this flexible platform, we can also use the PID auto-tuner blocks from Simulink Control Design for automated tuning. And by the way, if our DC-DC converter was not ready, we could also use the switches in the power module from Speedgoat. And by the way, if our DC-DC converter was not ready, we could also emulate the converter dynamics using hardware-in-the-loop testing. To develop a controller for a grid-tied three-phase inverter, we'll start with desktop simulation, including the solar panel, the inverter, and the grid. Once we're happy with the desktop simulation, we generate C and HDL code automatically from Simulink. We can then test our controller for the grid-tied inverter by connecting it to a Speedgoat target computer. In this case, we'll use a Synergia 2-level 3-phase inverter with an LCL filter for prototyping the power electronics part. Developing a grid-tied inverter is a complex task that not only involves expensive hardware, it also could affect the grid and other of its users. We can de-risk the development process with model-based design. We would start with desktop simulation involving the plant and the controller. Then rapid control prototyping provides a reliable test platform with proven I/O connectivity and the capacity to measure and change parameters on the fly. Once the embedded controller seems ready, it is still important to use hardware-in-the-loop testing to validate and thoroughly test under all operating conditions and fault conditions. It is just then that we deploy using production code generation to an embedded platform. We can learn more about this topic in a MATLAB Expo talk on grid-tied solar inverters. For doing rapid control prototyping for a grid-tied inverter, we could use a performance real-time target machine, including a large amount of low latency analog measurements. In this case, we use Speedgoat analog I/O modules with DMA memory access to achieve the lowest latency with multiple measurements. We also use a configurable FPGA I/O module including several FPGA code modules like PWM generators. We also have interrupts that are used to create a link between the PWM and the analog signals to make sure that we always measure currents when the transistor in series is properly closed. A measurement would not be valid otherwise. The Speedgoat interface from the Synergia power converter includes connectors for Speedgoat cables to transfer both analog measurements from current and voltage and also to provide access to the gate drivers via PWM switching or similar. The power converter interface also includes electrical protection features like overcurrent protection that provides an additional safety mechanism. For this example, we used a 15 kilowatt 2-level 3-phase power converter from Synergia, but as Diego previously mentioned, there are compatible interfaces for projects requiring from a few hundred watts to around 160 kilowatts. We also have two interesting success stories on rapid control prototyping. First, the Supergrid Institute in France, who leveraged a Speedgoat system to develop a new high-voltage, high-power DC-DC converter with rapid control prototyping. This DC-DC converter shall support efficient DC-DC transmission in supergrids, requires switching frequencies of 20 kHz, and uses silicon carbide transistors. In summary, a prototype dual-active bridge was built and tested within 1 year using real-time systems from Speedgoat. It is compact, can handle powers of 100 kilowatts at 1 kilovolt voltage, and has an efficiency of 98%. For testing and tuning the controller, a Speedgoat Performance real-time target machine served as flexible and powerful control unit. The controller was deployed to a Speedgoat multi-core CPU with Simulink programmable FPGAs. They included analog and digital plugins directly connected to the FPGA. Such FPGA plugins can handle signal conditioning in the range of a few nanoseconds and were used to drive the gates of the silicon carbide MOSFETs. Let's conclude with the case of Microsemi, now Microchip. Their Aviation Center of Excellence in Ireland faced the challenge to meet stringent reliability, size, weight, and cost targets of power core modules for electric actuators in the aviation industry. They use both rapid control prototyping and hardware-in-the-loop testing to develop and test intelligent power modules, enabling to push design limits by simulating failures, optimizing performance, and reducing risk with early-stage tests. The results were successful with the development of a motor drive solution for an aileron application, with Shane O'Donnell from their Aviation Center of Excellence finding that Simulink Real-Time and Speedgoat hardware enabled them to demonstrate the application-specific reliability of their early designs without having to install the unit in the actual aircraft. At the end of this webinar, there are 3 key concepts that we would like for you to take with you. First, that rapid control prototyping is a key step before using your final embedded platform. It de-risks commissioning with large processing power, on-the-fly parameter tuning, and Simulink-based data logging. It is thus ideal to de-risk commissioning of controls for costly power electronics hardware. Second, that as simulation and reality don't really match always 100%, automated tuning of PID loops and field-oriented control auto-tuning enables a smooth transition from desktop simulation to control deployment, as you can use them with real hardware. And third, that the Speedgoat and MathWorks real-time solution provide a platform that scales with the increasing complexity of your project, the processor, multiple FPGAs, communication protocol, and a wide range of I/O capabilities, therefore helping you find the right hardware. Thank you.
You want to learn more about real-time controls testing? Then find additional content linked here.